Okay, we will start in maybe around 2 or 3 minutes while we waiting for the other students. We will start the course. So, so I will start with the GeoGebra. Okay, so I hope you can see GeoGebra interface. What I want to show you is some visuals for a quadratic surface. So in this searching box here, you can search any type of topics, mathematics, calculus, any topic in math and calculus you can find. Wait a minute. Okay, so let's write a quadratic surface. You can find resources. For example, if you can find the 3-dimension application for a quadratic surface. For example, let's say we are trying to open this one. Okay, and then this is what it's look like. So this is basically what the most of quadratic surface really looks like in the in 3 dimensions. Okay, you have a conic sections, a cone. Okay, the red one is cone. The blue one, like this one, is the paraboloid, and the green one is the cylinders. And the yellow one is the ellipsoid. So if I uncheck the visuals, you can see the ellipsoid, but it's like a sphere now, because all the directions have the same distance. Okay, so it has the same radius. Okay, if you're going back and look for other sources, we can also look up to another one that is, I think, more complete. The previous is, I think, not really complete. And all these resources are free, so you can check all these resources. Okay, and you can check also other resources such as all chapters in your calculus. Okay, so I hope you try at least once. Okay, so you have at least intuitions to what the quadratic really looks like. So let's say we open this one, and you can check. For example, this one is a cone. Let's say we have a cone here, and we can change to ellipsoid. This is ellipsoid. We can zoom in and see what this looks like. Okay, we can see this cylinder like that. That's our cylinder with an ellipse as the surface area. And we can see just a plane like that. Like we have discussed this in the first introduction of the vectors. And this is the hyperboloid. This is just one hyperboloid, and then this is the second one. Okay, this is the hyperboloid one sheet. Okay, if you remember, a one sheet hyperboloid. We can change the coefficient, can make it bigger, smaller, and then like that. Can make it different shape. And let's look from some distance here. So this is how it looks like. That, and maybe I need to move out the X to maybe a little bit there, and maybe a little bit here. And if you see the hyperbolic paraboloid, this is what it looks like. It's a little bit cut down by this cube. So if you see it, if I maybe, okay, a little bit there. Wait a minute. Okay. So you can check one by one, and let's see another one. This is a parabola and cylinder, hyperbolic cylinder. This is the paraboloid. And then cylinder, ellipsoid. You can also make some animations. You can try to move out and see what's the different. And you can also change like the information from these equations. Okay. Yeah. Let's see other resources so that you can have some idea. Let's say this one. And each of this, they have some explanations how to use that. And you can change the coefficients in any number you want, right? So this is the ellipsoid. the hyperbola of one sheet. You can make it smaller. Yeah, make it smaller so you can see the shape. Okay, so it has a hyperbola here, hyperbola there, uh, in the one axis, and this is a hyperboloid of two sheets. You have a hyperbola here, but it kind of split the graph, right? Okay. And you have the, I think, elliptic cone. I haven't said anything about this, but this is, I think, quite simple equation. So you have an ellipse here, but when you look at here, it's like you have a line, and then you have like a plane there, okay? Like a plane there, right? But it's actually an ellipse. Okay? So it's called elliptical cone. And this is the elliptic paraboloid. So you have, here's the ellipse, and when you look at here, it's kind of having parabola shape here. And then the last one is the complicated one. This is the hyperbolic paraboloid. So maybe I need to make it bigger there. Yeah. So it's like a saddle, but in here it's kind of reverse, like that. So it's like a saddle. So I hope you can see this picture clearly. Okay. So here's the middle one here is the saddle point. So it has, here is, you can see the hyperbola is in the left, right, and top and down. Also, they have a parabola, a hyperbola, right? But when you look here, the hyperbola is actually in the top one here and down there. Okay. So if you are rotate that, you will see it also has, first is the parabola here. You can see parabola, and you can also see parabola here. Okay, so that is the shape. Okay, so I hope you get my point. Getting more understanding in the quadratic surface, and I hope you can check the quadratic surfaces by yourself. I'm not sure whether you can check with this link, but you can try out this. Yeah, you can check that link, or if you cannot use that link, just go to GeoGebra and searching by yourself, look for quadratic surfaces, and you can check the graph by yourself. Okay, what I want to see here is, again, when you are changing the structure of the equations, you will see the equation in the left here, in the bottom left. If we are changing a, maybe going to smaller, it will also affect the picture like that. Let's go to 5 here. But what the what makes different in quadratic surface is the notations. Okay, so you have this equation now. You will see it has squared in x and squared in y, and then z is not squared, it's just a linear. And in x it's negative, in y is positive. So whenever you find one axis is negative, one axis is positive, and it has squared, then it will be a hyperbolic parabola. Let's see the simple one, the ellipse. If you see this, you have the x squared, y squared, z squared, and all is having squared, right? that's becoming an ellipse, and they don't have any alternating signs, so it's all positive. Okay, you have the hyperbola of one sheet, so it has at least one alternate sign here. It's negative. But for the hyperbolic two sheet, it has two negative, one positive. So that's the different. Okay. And elliptical cone, it has two positive square and one negative square. The difference is, let me make it more clear. The difference is just this is 0 and this is 1. And we have a paraboloid here, and you can check by yourself. Okay, let's go back to some notes for you, and then maybe finishing the chapter 12. Okay, this is the last time we discussed the chapter 12. Let me add something, and then we can go to some intro for chapter 13 and we exercise for your midterm. Okay, so summary for 12.6, the quadratic surface. So first you have the shape called ellipsoid. It has this structure. If A equal B equals C, then it will be a sphere. And the shape is, let me just draw the that's the ellipsoid. So all traces is an ellipse. Okay, so if you see any of this kind of equations, okay, the structure is similar like this. What you need to do the first time is ignore one part, and you'll see the conic section ellipse. Okay? And then do the again for the other parts. You'll see another ellipse, and you do for another part, and you'll see the same ellipse. Right? This is the easiest one, I think. Okay, the second one is the elliptic paraboloid. Okay, now elliptic paraboloid, it has 2 squared here, x squared and y squared. It can be x squared, z squared. It can be y squared, z squared. It's okay as long as it has 2 squared and 1 linear like that. So it will be like that. Okay. Hopefully you can see this shape like this. If you trace the parabola here, you can trace it like that. Okay, but I think I don't need to trace to draw it. Maybe you will find it confusing. So horizontal trace are ellipse. So you can cut each horizontal here, and you can find the ellipse in the cutting. And the vertical traces are parabola. And this is in z-axis, right? So if this is the axis here, this is z. Okay? So the power here, the one power here, it's indicating the axis. Okay. The third one is hyperbolic paraboloid, the complicated one. Has it has hyperbola shape and then parabola shape. So horizontal trace are hyperbola. Vertical traces are parabola. Okay. Oh, I think it's better now. Like compare with my drawing last time. Okay, so this is the axis is here. And there. Okay. Maybe a little here. Okay. And it has a parabola here. Okay. Okay, that's the hyperbolic parabola. So remember, it's not always in like x squared, y squared. It can be x squared minus c squared and then y c. That's possible. Or y squared minus z squared and then it's x. It's also possible. Okay. So another part is called cone or elliptical cone. The shape or the equation is similar to elliptic paraboloid. The difference is here we have z in squared. picture is not too difficult. Okay. Horizontal trace is ellipse. Vertical traces is pairs of lines. This is if k is 0. Z, oh, wait, x is k and y is k. If k is not 0, then it will be hyperbola, which means it will be like this. Okay. Okay. Let's move on. Okay, so ellipsoid, elliptic paraboloid, hyperbolic paraboloid, and a cone or elliptical cone. Another two. Let me add. 5 is hyperboloid of one sheath. It's kind of similar from the equation compared with the previous one, the cone, but it has equal 1. Okay. So horizontal trace are ellipse. Vertical trace are hyperbola. That's what I'm talking about before here. So if you have a pair of line, but if it's changing, it will be an hyperbola, like what we will draw next in the next page. Okay. So it will be like that, like that. Okay, it's not too smooth, not really like an ellipse. I hope you can see that it's an ellipse here. Okay. So you will see that in this part, this is the negative, right? The z is negative. So, and you will see that here, z is in our axis here, right? This is axis z. So the one who has negative will be the axis that the hyperboloid of one sheet will be. So for example, if I have y, x, and then not x, maybe z, and then minus x, this is equal b, c, a, and equal 1, which means this is I will have in x, like that. So this is x, this is y. Okay, I hope you get it. And then the last part is the hyperboloid of two-sheath. It's kind of similar with the one-sheath here, but the difference is the alternate signs. So it will start with x as a negative x squared, and then negative y squared, and then plus z squared. So if you have 2 minus sign, 2, which means that will be our hyperboloid of two-sheath. Okay. Okay, hyperbola of two-sheath, the horizontal trace, and if you make z as constant, this is ellipse. If k is greater than c, or if k is less than negative c. Okay. Which means you have two parts here, right? This is greater than c, this is negative. Okay. And vertical trace are hyperbola. This is the hyperbola. Okay. And this 2 minus sign indicate two-sheath. And this positive becoming the axis. Okay, let me explain one more time, okay, so that you can get the idea clearly. Okay, so first, it's the ellipsoid. All the terms are positive, 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 okay, and all has x squared, y squared, z squared, and equal 1. Okay, this is the easiest one. The elliptic paraboloid starts with x squared, y squared, and equal a linear, just z. It can be y squared plus z squared equal x. And this linear part is becoming the axis. Okay. The third one, the complex one for the shape, it starts with the shape of hyperbola, positive x squared minus y squared, and equaling the z. And again, this z becoming the axis, z. Okay. You will see that this is the hyperbola. Hyperbola is here, here, and here, and also here. And this is the parabola here. It's from the x squared equals z. And this is negative y squared equals z. Okay. Okay. Now the fourth one is the elliptical cone. So you have this, an ellipse, right? This is ellipse. So ellipse is from here, the ellipse. And Z here is also in square, and the one here is becoming the axis. Okay, and you see that it has two ellipses at least. You'll see here two ellipses, right? So it can be, if you could trace from the origin, it can have two ellipses. Okay, it can trace here and trace there. So two ellipse because Z can be positive, can be negative, right? Okay, now the last two is hyperbola of one sheet. It's kind of similar, both of this. It's kind of similar. The first one is having two positive sign, and the last one is having two negative sign. Okay, and the other sign, the this one, the positive sign become the axis. This one, the negative sign become the axis. Okay, I hope you get it. Okay, for the next one, I need to go to chapter 13. Okay, chapter 13, just an intro, just a few intro, and then we can go back to our exercise. Okay. We will have maybe some exercise for chapter 12, maybe later. Okay, is there any question from here? From 12.6? If no, let me explain for chapter 13. So chapter 13 is, its title is Vector Functions. Okay, so because chapter 12 we learned about vectors, and most of the time we already learned about functions, the calculus 1, calculus 2, right? So what does it mean is actually we will use all the calculus in terms of vectors. So a vector function maybe a function whose domain is a set of real numbers and whose set is a set of vectors. Okay. Which means for every number, let's say parametric t in domain of, let's say, R, like that, there is a unique vector. And I will write v and 3, which means in the space, okay, 3-dimensional space, denoted by RT. Okay. If, okay, let's say FT, GT, and HT are components of RT, then we can write RT And we can write also in terms of standard basis vector. Okay. So if example, okay, so if RT is, we have a functions inside the R, the component FGH. So FT is T cube, GT is ln3 minus T, and HT R squared of T. And to check the domain, we can also check the domain. Um, we can check in this ln because that is our restrictions, right? The ln. So we need to have 3 minus t is greater than 0. And then this is also need to be, t need to be this, right? So domain will be from 0 to 3, but open it, close and open. Okay. Okay. That's the intro, and maybe one conclusions here. Let me write here as a conclusions for limit and continuity. If then so by definitions, we are taking all the components with limit. And provided the limit of component functions exists. Okay. I think that just set up some definitions. Okay. So again, let me explain one more time. So a vector functions is a function we can set in a real number, and the range is in a vector. Okay. So we are usually using in terms of this R for a vector function. So usually we say R equal this component F, G, and H. Okay. And this is just an example to find domain and the to find the domain of our vector functions. And all the concepts of calculus 1 will be also using in here in the vector function. So for example, the limit here and continuity. For example, in in the calculus previous semester, we say that some functions will be continuous at some point if the limit is equal its or let me write here. Maybe you will remember. So a vector function r, okay, is continuous at a if the limit is equal the function at that point. Okay. It's continuous, right? Which means if you have line, there is nothing that block or disrupt, right? Different from if we have like line like that, and then we have a hole there, then it will make not continuous, right? It's become not continuous. Okay, I hope you remember this concept of limit. Okay, maybe one more thing, and then we can finish the chapter 13 for now. And one more thing, in chapter 13, we will see the space curve, the term space curves. Okay, suppose f, g, and h all is continuous function on some interval I. Then set C of all points of x, y, z in space where x is ft, y is gt, and z is ht, and the t is varies through interval I. Now this is called the space curve. And these equations here, x, y, z here, it's become the parametric of equations C. Okay, and t is our parameter. So this C, we can think like a curve that being traced. For example, okay, I will draw a really random curve. So for example, in 3-dimension, let's draw some random curve. Let's rename this C, X, and Y. Okay, let's say we are moving somewhere here. Okay, and we have the direction because it's a vector. Okay, and we are tracing one by one. Let's say we are tracing at this point, here, point P. Okay, and let's say the R is a vector of FT, GT, and HT. And at this point P is our point, our coordinate of FT, GT, and HT. Okay, it seems similar with this one, but it's different. Okay, this one meaning the position of vector will change throughout the curve. For example, this point P here is the coordinate, okay, the vector position, or the position of the vector, or the coordinate of the vector. So the coordinate of the vector will change throughout this arrow here, this line. They will change throughout the curve. Okay, I hope you get the idea. And this means in this picture here, C is traced out by the tip of a position vector, RT, okay? And like, if you have RT equal 1 plus T, 2 plus 5T, and minus 1 plus 6T, you can describe this in terms of what kind of curve will it be in our 3D space. And we can see from the equations, this all will be in the parametric. This is x, y, and z. And we can check the positions through that parametric equations. And it will be align equations, right? And we can also trace out in curve C. Okay. Okay. Now I will end the chapter 13 part here. So any questions? If no, then I will move on, because I'm not really sure whether you understand the chapter 12 or chapter 13. Okay. So let's just go to review the chapter 10 and 11 for your midterm. Maybe let's just have some exercise, and I will give you some questions. Let me give you the questions. Okay. The first question is, which of the following statements are always true? Let me give you the options. A, if the series if this is converged, then this converge. And B, if both A and B and convergent, then And if n is greater or equal 0, maybe just this. Okay, the first one, you can try it. Okay. Anyone uh, try the solution? It maybe it will be more than one answer. If you solve this, you can write down the answers in the chat box. Okay, anyone solve? Okay. Hello, everyone. Everyone solve this one? Can you write down your answer in the chat box? Okay, the questions: which of the following statements are always true? A, if the series you have absolute an plus an converge, then an series an will be converged. B, if both series an and series bn is convergent series with positive terms, then the series of an multiplied by bn is convergent. C, if an is greater than 0 and limit as n approaching infinity of n squared multiplied by an is 0, then the series of an is convergent. If series an divergent, then series of an squared is divergent. So what's the answers? Have you tried to check? I will wait until you write some answer in your chat box. Trevin, A and B. Okay. Mm-hmm. Any other answers? It's half correct. Half correct. Okay, let me step by step explain, and then I will give you some more time to also rethink the answers. So if you answer A, let's check the answer A. So let's say the series is this. Okay. if the series an or the sequence is negative n. If we put here negative n and negative n, this become positive, right? And it will be 0, which is converged, right? But this series, this negative n will diverge, right? Okay. So it is contra uh, solutions. So it's wrong. Okay. So A is false. And B are correct. B are correct because A and Bn is positive term. We can say that this will be greater than 0 or equal 0 because 0 is also positive. And this will be less than, we can split up the A and Bn, and it's always true, right? So that's why it's always true, it's converged. How about C and D? If we see the numbers, the option C, so let me write the limit. This is actually from limit comparison test. Okay. So if the result is having a positive value like 0, 1, 2, 3, and so on, uh, the let me write the limit comparison test here. C, it's positive value. So if this is the limit comparison test, then if Bn is converged, then it's also converged. If this is diverged, this is also diverged. Now let's look here. We can write this in terms of, let's say, an and 1 over n squared. So the 1 over n squared is converged. Then this an is also converged. So C is also true. So this is true. It's converged. Now let's see our option D. So first write if this is diverged, then what is this, right? Is this also diverged or something else? What happens if your an is 1 over n? Well, this is true. It's diverged, right? It's diverged. But when you square it, it's become 1 over n squared, which is becoming converged, right? So this is not always true. So it's false. So D is false. So the one that stays true is B and C. Any question from here? If not, let me give you another one. So the question is just find a surface area. Okay, that is the second question. And the second question for this one, I will add another one. Find the sum of this series. Okay, I think the surface area you need to, I think as long as you know the length, the arc length, uh, the surface area is just adding the 2 pi x or 2 pi y in the front of the arc length and then integrate with the respect of parametric from 0 to 2. So let me write the answer for the surface. So this is just because it's rotating through about x, so it's x, and then dl or ds, it's the arc length, and then you can write this as 2 pi, and then x is et minus d, and then ds is the square root of the first derivative and then squared the x and y. So this become et minus 1 for x, and for y it's become 2 et over 2 and then squared and dt from 0 to 2. I hope you can solve this. Okay, I hope you can please solve this by yourself. Okay, it should be not too difficult. Okay, you need to um, use some set of algebra, simplify the form, integrate, and that's the answer. Okay, please solve this. And if you want to check the other questions that it's more interesting, this number 2 here. If you want to focus on this, that's good. You can check and try to find the sum of the series. So this is 1, maybe not too clear. Okay, so for number 2 here, you need to check between the 6 function that I gave you. The this, 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 tangent inverse. From all these 6 functions, you need to at least know how to make it. Okay. And then you need to see from there, you need to check whether this is suitable for applying the series. Okay. And because in the question here, you don't see any x, right? No x here, which means if you have, for example, the e to the x is having x and this, right? Let me just write that one. So because it's having some x here, meaning you need to find x so that you will get this result. And when you do that, then you can find the sum of the series. So if you want to know the answer for the previous one, the answer is pi a to the 4 minus 9. Okay, let me start writing down the second one. Okay, let me copy this first. So you need to find the sum of the series here. So first, the idea came from matching the functions, and my suggestions, and of course this is the answer, is using the tangent inverse. So if you write the tangent inverse, okay, this is for x is less than 1. Okay, now we need to find x. Okay, find x that suitable for the question. So which means we need to find x so that we can put into here, put into the tangent inverse. Now to narrow our selections, we need to see the tangent. At least try the from 0, pi over 6, pi over 3, pi over 2, and maybe pi over 4 here, and pi. Maybe we could try either pi over 6, pi over 4, pi over 3. Okay. If we check tangent pi over 6, we will have or we can just write this as 1 over square root of 3, right? If you have pi over 4, it's 1, right? If we have pi over 3, we will have square of 3, right? Now, the question is in the tangent inverse. So we need to make it into inverse form. So tangent inverse, right? Okay. And this is our option for x, right? All these three. Let me erase that again. Okay. So if you see here, it has 3 here, right? The possible solution is either the first one or the second one, because it is a fractions a over b, right? And 3 is somewhere here, so probably we are going to use this one. That's how we are going to narrow our answer. Okay, so we can write 4x is equal 1 over square root of 3. We have tangent inverse like that, and we input the x inside the series. For number 1, oh, sorry. Let me check the question. Oh, yeah. I think the question should be in uh, wait. Yeah, it should be y-axis. Yeah, sorry. I'll write the wrong question. See, should be y-axis. Okay. Yeah. Good. Yeah, if this is x-axis, then you need to multiply with y. Okay. Good. Okay, back to the questions here. Okay, now we are going to add and replacing x with the 1 over square root of 3. Now this is 1 over square root of 3, and then square with the power of 2n plus 1, and this is 2n plus 1. Now, step by step, we are trying to simplify the form and see if we can rearrange the form and make it into our solutions. Now, this is, I can write this as 1 over 3, right? and this will be n, and multiply with the 1 over square root of 3, right? Now let's do that. And because it's a fractions, let's put 3 on the numerator. So we will have 1 over 3 with power of n, and 1 over square root of 3. And this is the alternate sign. And 2n plus 1. Now we are getting closer to what we are looking for. So let me write this as tangent inverse. Oh, why I'm writing this twice, sorry. And then we are writing, this is the alternate sign. And then 2n plus 1 here. Let's move here. And let's put our all constant. Put all constant outside of the series. So this, yeah, like that. And 3 with n. So we have now our sum, right? This part is already the same as this part, right? And we need to finish these equations and find what is the sum of this series here. So tangent inverse of 1 over square root of 3 is pi over 6, right? So this become pi over 6. And 6 I will move to the right side, so it's become like this. And write down the series. And now the series is equal this is pi minus 6 over square root of 3. Or if you want to simplify this, become 2. Yeah. Or if you want to make it into this form is also fine. Yeah, but I think until here is already the answer. Okay. Okay, any question from here? This is quite long, I think, because the difficult part is to get in touch with this tangent inverse. If you cannot make it to here, then all the answer here will be difficult to follow. Okay. So first, you need to find out. The clue is the 2n plus 1 here. So it's nothing to do with factorial, right? So we will skip the sine and cosine, right? So 2n plus 1 is exclusively for the tangent inverse here. And the rest is we need to check which x that is suitable for our solution. So we check the tangent that can be put into the equations. So we are check that the one that is uh, available is this and this. That will make 3 here, okay, at least. So we are trying to use this or this, but I think here is more suitable because it will be 1 over something down here, right? So that's why I'm choosing this one. And by doing that, we are solving the x as 1 over square root of 3 into the equation of the tangent inverse. And step by step, we are getting closer to our solutions, which is this, is the original equations, right? So from here, what we are going to do is just solving the tangent inverse, and we are solving this equations, and it's equal to this pi minus 2 square root of 3. Okay. Okay, any questions? Yeah, I think this number surface area here is correct that you mentioned. Should be it's y-axis, so that this is x. Okay. If this is x, then this should be y. Okay. Maybe one more questions, but I'm not sure whether we can finish that questions. Let me write the questions here. Let functions g is this, and if t is not 0 and g 0 is 1, and f of x is integrations of this g, then the question is f5. So f5 means derivative fifth terms. Does n equal 0 and n equal 1 matter the form of equation? Yes. It will shift the series. So for example, let me check the questions. The questions is actually is equal 1, and the oh yeah. I'm just missing something here. So let me put down here so that it will be, so it's 2 square root of 3. So if I put n equals 0, it should be 1, right? So I can write this as 1 plus Yeah, good observations. Because when you put n equals 0, it will be 1, right? So let's just erase this part. So this will be um, this part will be and we need to solve through here. So it will be pi over 2 over 3 minus 1 or pi minus 2 over 3. Okay. So yeah, n equals 0 and n equal 1 um, will be affecting the equations. And good observations. Yeah. And fortunately, the if you put n equals 0 here, put n equals 0 here, put n equals 0 here, it will be 1, right? So that is, I'm writing 1 here. So I forgot to write this. Okay. And the next part of the series is start from n equal 1, which is our question n equal 1. Yeah, sorry. I forgot. I thought it was 0. Yeah. So if that happened, then you can make it like this way instead of, so sometimes if you want to change from here to here, you can shift the n. Okay, like for example, n plus 1 become n, or n plus 2. It's also applicable. You can also choose that way. But because when we check here sometimes, okay, if we check n equals 0, is there is nothing wrong and it's just 1, then I'm suggesting just to use this form. Okay, it will be easier rather than you are changing this n, all this n. Okay, like maybe n plus 1 and minus 1. You can shift that. Depends on which n you want to observe. Okay. Okay. I think this one you can write down and try as exercise for you. And because we are now, I think we don't have much time. I think it's already finished in 10 a.m. now. So you can write this as your exercise and try some questions from the textbook also. Okay, I think that will be our end of session. So yeah, thank you for your attentions, and yeah, thanks also for observation of some questions. Okay, good observations. So I think that's it for now. So I will stop the recording, and you can leave the meeting if you want.